Next speaker will be David Madigan, Columbia.
Thanks, Rich, and thanks to the organizers for inviting me. I'm very happy to be here. I'm going to talk about some work that I've been involved in for the last several years. Parts of this, some of you in the room, a handful of people will have seen before, but if you hang in there, there's some of it you have not seen before. The work I'm going to talk about took place mostly under the auspices of a project called OMOP, the Observational Medical Outcomes Partnership, which was a public-private partnership between the FDA, the Food and Drug Administration, and the pharmaceutical industry. And that work is complete, but it now continues under the auspices of Odyssey, this OHDSI. And the point of that is those two websites basically have a lot of materials pertaining to everything I'm about to talk about. So I'm going to talk about observational studies in healthcare. Whether this is big data or not is in the eye of the beholder. We're working with data on very large numbers of patients. And I'm specifically going to focus on healthcare. I'm actually going to more narrowly focus on the causal effects of drugs, basically. So there's a lot of excitement in the air in the world of pharmaceutical research and regulation about big data, about big healthcare data. Consider the drug metformin. It's a widely used drug for diabetes. Supposing you wanted to study a potential bad side effect of metformin, let's say there was a concern that it might cause a certain type of cancer or whatever. Well, if you go back to the randomized trials that led to this drug being approved, and there were such trials decades ago, in the pivotal trial that got the drug approved, there were a grand total of 141 patients exposed to metformin. So if you're trying to make inference about any kind of even modestly rare side effect or effect of the drug, forget it. You're out of luck. Flash forward to where we are now. In the databases that I'm about to describe, we have over 1 million new users we can identify. Interesting. Over 1 million new users of metformin in those databases. So the excitement and the promise here is surely with data on this kind of scale, we can make inference about potential causal effects of these drugs, and that's what a lot of people are trying to do and are doing in various ways. I'm going to express concerns about some of those activities, but in any event, that's the basic idea here. Is we now have the potential with these kinds of data to get at causal effects of healthcare interventions that were not accessible heretofore. So what do these data look like? Actually, let me use the pointer here. It might be better. Here's the kind of data I'm talking about are electronic health records and administrative claims databases. So these are data that are gathered not for the purposes of supporting causal inference, like I'm going to talk about, but they're gathered either for routine medical care purposes or for billing purposes. I'm not talking about genomic data, and there's very interesting work underway in various places around the world on combining these kinds of healthcare records with genomic data and other kinds of data. So the kind of data I'm talking about that we've been working with, they look like this. So here's a record for a particular patient. This is time on the horizontal axis. That's a couple of years worth of data. So generally speaking, in these databases, we have information about visits, so encounters with the healthcare system of one sort or another, procedures. So this patient had a procedure here and a number of procedures in and around here. And of course, we know what the particular procedure was. We know about drug exposure. Basically, we know about prescriptions that the patients were given. We don't actually know that they consumed the drug necessarily. We have information about conditions, just diagnoses that were made as this patient encountered the healthcare system. And then in some cases, we have what you might call observations. Observations. These are lab values typically, so blood draws and what have you. We have a certain amount of lab data. So that's what a patient profile looks like. That's actually a real patient. That's not the real patient's picture, but that is actually the data of a real patient. And that's what a patient looks like. Here's another patient, another real patient. Here's another patient. So some of these get very complex, and in particular, people with a constellation of chronic illnesses, they have very complicated interactions with the healthcare system and have records that can look like that. But in essence, the basic idea here is I give you 100 million of these, or 600 million of these is what we now have in the union of the databases, and from that I basically want to figure out which drugs are causing which side effects. specifically. There are other questions one might ask, but I'm focused on drugs here. So that's it. That in a nutshell, that's what I'm about to describe is about. What can we do with lots and lots of these? So these kind of data are increasingly readily available certainly to researchers. They've been available for a while in various forms. So databases of this type, observational databases, have existed for probably 15 or 20 years, maybe a little further. And people have been publishing papers using these kinds of data for decades. So here's a typical study that you might see, and actually pick up any issue of a major medical journal, JAMA, BMJ, Lancet, whatever. You're going to find studies like this. They're all over the place, and we're all familiar with them. They hit the newspapers quite often as well. So here's a very typical study. This is a study of oral bisphosphonates. These are drugs to help prevent bone loss. They're taken by about 7 or 8 million people in this country. Oral bisphosphonates, and in this case, the risk of cancer of the esophagus, I'll focus on. So it's a causal inference question. Do oral bisphosphonates cause cancer of the esophagus? And the C word never appears in this paper. It never appears in most of these papers. But in fact, it's all we care about. But that is what this is about. So they did it, in this particular case, they did a case control analysis, which I won't describe it, but it's a very classical epidemiological design that's very widely used in a large-scale electronic health record database. It's a UK-based database. And they concluded in this large nested case control study with a UK cohort, we found a significantly increased risk of esophageal cancer in people with previous prescriptions for oral bisphosphonates. This was on the front page of the New York Times a short time later. Quite a concern, a significant public health concern. Round about the same time, there was another paper. This one was in JAMA, well regarded in both cases actually, but quite prominent groups of analysts. Exposure to oral bisphosphonates and the risk of esophageal cancer, exactly the same question. Among patients in the UK GPRD, the use of oral bisphosphonates was not significantly associated with instant esophageal or gastric cancer. So opposite conclusions, and the kicker here is same database. So two different groups of analysts analyzing, in good faith, analyzing the same database and arriving at different conclusions. One might think that this is a freakish occurrence. Au contraire, the bad news is this is very common, and you can find countless examples like this very easily. Let me flip through a couple of them. Oral fluoroquinolones and the risk of retinal detachment. Patients taking oral fluoroquinolones were at higher risk of developing a retinal detachment. Actually, same journal, short time later, oral fluoroquinolone use was not associated with increased use of retinal detachment. Pioglitazone and bladder cancer. This is actually a very live public health question right now. A lot of people take pioglitazone for diabetes. In this study population, pio does not appear to be significantly associated with bladder cancer. BMJ, short time later, use of pioglitazone is associated with increased risk of instant bladder cancer. I think those two papers also used the same database. I could go on. I have dozens and dozens of these. I make it my business to collect these examples. I'll just show one more. This is a very interesting and puzzling kind of situation. There are blood thinners. There are drugs out there that will thin your blood. Warfarin is the one that's been around for decades and is very widely used. And people who are at higher risk of stroke are often prescribed these blood thinners. Blood thinners increase the risk of bleeding, mechanically, so to speak. But in any event, warfarin is problematic. Is a difficult drug to take because you have to continually monitor various issues to do with something called INR, and it's a nuisance. So there are newer drugs that have come on the market, so-called NOACs, novel oral anticoagulants, that are reaping in billions of dollars of revenue for drug companies. And this is in the last 3 or 4 years. One of these drugs is called dabigatran, and shortly after it was released on the market, the FDA was flooded with with reports of major bleeding on dabigatran. So the FDA did an analysis in one of these large databases, actually a distributed collection of databases called Mini-Sentinel, and they released a risk communication about the bleeding risk of dabigatran, saying that basically it was fine. It was actually better than warfarin with regard to major bleeding. They then published that in the New England Journal of Medicine. It was picked up by the company. It was on the company's website nanoseconds after the FDA released this risk communication. But there's a very interesting, there are a number of serious problems with this analysis, and I'll get into this a little bit as I go along. But Jerry Avorn from Harvard published an essay which is just a beautiful piece of writing, where he said, however, referring to this study by the FDA, however, the absence of any adjustment for possible confounding, it was an unadjusted risk ratio comparison, if for those of you who are into these things, completely unadjusted. However, the absence of any adjustment for possible confounding and the paucity of actual data made the analysis unsuitable for informing the care of patients, which, so it sounds sort of benign, but if you actually think about that for a second, it's very problematic that the FDA is releasing this risk communication when some folks, and I would absolutely agree, would say this is really not the evidentiary value of that analysis is very modest at best and should not be used to guide patient care. Sometime later, there was an interesting analysis showing that the FDA's analysis was completely at odds with what the randomized trials showed in this particular case. All right, so we have a problem here. We as a society are relying to a great extent on what we think is evidence coming from these kinds of studies, but there's certainly some evidence, I just showed it to you and I'm about to show you some more, that there are real concerns about what we're doing here. I would claim that the process I'm describing here has essentially completely unknown operating characteristics. By which I mean the process is, you start with a clinical question. Oral bisphosphonates and esophageal cancer, is there a causal association? You decide you're going to study this in a certain database, you cook up a certain analysis, you make myriad design choices that lead to the particular analysis that you execute, and then you output some statistical artifacts. You output a confidence interval or a p-value or whatever. So let's just focus on the confidence interval. So you output a 95% confidence interval for the relative risk or the odds ratio or the effect size. Right? So what you would like is, when I talk about operating characteristics, what you would like is that confidence intervals of that type contain the truth 95% of the time, right? Or at least approximately 95% of the time. That's the whole idea here, right? So in actual fact, we have no idea what the coverage is of confidence intervals from these studies. Not a clue. I'm going to present some evidence in a minute or two, but I would claim that we really have no idea. Do they cover the truth 92% of the time, 97% of the time, or maybe it's 20% of the time? So we don't know. We're using these, we're following this process, studying these issues, and we have no idea what the operating characteristics are. Anna Scharfman at the FDA made an analogy which I find very powerful, which is it's like the early days of lab testing. So 20 or 30 years ago, if you wanted to measure a total cholesterol or a white blood cell count or whatever, you gave a blood sample to your favorite lab technician, and they came back and they said 73. And you had no idea what the operating characteristics are of that process. Is it likely to be within 2 of the right answer or within 50 of the right answer? You have no idea. That is not the way it is now with lab testing. Labs in this country around the world are highly regulated, and they routinely run test cases, positive controls and negative controls. We have a very good handle on the operating characteristics of routine lab measurements. We are not there with these kinds of studies, these kinds of observational studies in healthcare. What it really is you go to your favorite epidemiologist or analyst, they go away, they do something, they come back, they present you with an estimate and a confidence interval, and it's, trust me, I'm a good epidemiologist, I know what I'm doing. That's where we are with these studies right now, and I think we desperately need to get to a better place and generate what I would refer to as honest inferences from these kinds of studies, because right now they're not very honest. And I'll put some flesh on this as I go along here. Okay, so I'm going to describe some work that took place over a 3 or 4 year period, finishing a couple of years ago, that basically tried to get a handle on the question, how well do these studies work? What are, from some perspectives, what are the operating characteristics of these kinds of processes, of going about studying questions in that way? So here's what we did. There were a large number of people involved in this, and there continue to be a large number of people. So I'm going to describe it as if it's my own work. It's not really. There are at least 30 people involved in this project. Okay, here's what we did. We acquired 10 large-scale observational databases. This is a mix of electronic health record databases and claims databases. You can buy these data. We mapped the data, and the union of the databases contains about 200 million lives. We mapped these data to a common data model, and therein lies a complex story that I'm not the person to describe, but there are issues and pros and cons of different ways of doing that, but we mapped them all to a common data model, including crosswalking different dictionaries and what have you. It's a non-trivial exercise. We implemented in open source software a methods library, which is basically we implemented in software every major method that is in use, routine use for these kinds of studies. They're not terribly esoteric. They're sort of vanilla designs, case control designs, nested case control designs, cohort studies, self-control designs, case crossover designs, and so on, in software in such a way that they would run to scale against these databases. We set them up in such a way that the design choices, or at least some of the design choices that analysts routinely make in doing these kinds of studies, were essentially parameterized. So they were external to the software, so that we could run analyses with essentially different settings of the design choices that analysts make. I think of them as knobs. So different, there are many choices. Like in a case control study, how many controls per case? How do you match the controls to the cases? What do you adjust from the logistic regression? What are exposure windows? And on and on and on. There are dozens of design choices that analysts make. We then developed, and this is the heart of the matter, we developed a set of test cases. So we developed a set of drug outcome pairs. In this little cartoon here, these are drugs across the top, and these are outcomes on the rows. We developed a set of test cases, like, for example, the one I'm pointing at here is warfarin and bleeding. That's a positive control. We believe, with a very high degree of confidence, warfarin causes bleeding. It's a blood thinner. It's not a very controversial claim that warfarin causes bleeding. Equally, we have negative controls. So, for example, ACE inhibitors and aplastic anemia. That's a negative control. There's no evidence anywhere of any sort in any clinical trial or any observational study or any spontaneous report database that there's any association between ACE inhibitors and aplastic anemia. ACE inhibitors have been around for a long time, so we feel comfortable saying that's a negative control, meaning there is no association. The true relative risk is 1, or very close to 1, right, between ACE inhibitors and aplastic anemia. We could have a long conversation about the process we used to craft these test cases, and that, there are real valid concerns about this, but in any event, we crafted about 400 test cases, about 250 negative controls and about 150 positive controls. And then we did a big bake-off. So we ran all of the methods, configured with basically a full factorial design, all the possible design choices, all told about 3,000 different analyses. So we ran all of the methods against all of the databases for all of the test cases, to see basically how well, on some level you can think of it as, how well do different methods and different databases do at discriminating between reds and blues, between positive controls and negative controls. So on some level it's a very simplistic kind of a design, but it was just a preliminary step that had not been done before, as far as we know, to get a handle on how well does this work. So we learned some. I'm not going to go through, it would take me quite a while to go through this in detail. I'm just going to highlight some of the lessons we learned from this exercise, and then I'll finish by just talking about some of the current activities that are going on. So some of the lessons we learned. Here's one lesson we learned. So here what I'm showing is, this is for a particular outcome. It's acute liver injury in a particular database using a particular method. It's set up in a particular way. It's the cohort method with high dimensional propensity score matching. What we're looking at here are confidence intervals for negative controls. So for negative controls, the true relative risk is 1. So 95% of the intervals should contain 1, and 5% of the intervals should not contain 1. That's what the coverage should be. There are 34 negative controls here. In actual fact, the coverage here is around about 50%. So the 95% confidence interval actually contains the truth about 50% of the time. And across the full range of analysis that we did, it varies by outcome, it varies by database and so on, but typical 95% interval coverage was in the 40 to 60% range. This is very problematic. Right? So essentially the confidence intervals we are publishing don't mean anything. And we have no business publishing them. We're just deluding ourselves and thinking that they represent quantified evidence. They don't. There are references I can give anyone for these studies. Lesson number 2, one of the things we were able to look at, because we were looking at 10 different databases, was database heterogeneity. Do you get different answers when you run exactly the same analysis in different databases? Here what I'm showing is there are 50 drug outcome pairs on the rows, so it's like 50 different studies. And for each one of them, this is a particular analysis. This one is also high-dimensional propensity score matching, set up in a particular way. The dots represent the point estimate from, ignore the colors for now. The dots represent point estimates from different databases. And you can see, for example, the ones at the top, across all of the databases, you get, that's the vertical line there is 1, a relative risk of 1. So for the ones on the top there, no matter which database you run it on, you're getting at least a positive estimate. You're saying that the estimate is bigger than 1. But cast your eye up and down, and what you see is, and it varies by method, but typically, about 30 to 40% of the studies, you can go from statistically significant in one direction to statistically significant in the other direction, depending on which database you use. Now, there's nothing mathematically remarkable about this. These databases are different. They represent different populations. They're just different in very many ways. But I'll be darned if I can find a paper out there that gives a detailed discussion of why the analyst chose their particular database. It's just, we used the Kaiser database, or we used the GPRD. And in fact, what we're seeing here is, had they used a different database in some of those studies we were looking at a minute ago, they might well have gotten a different answer. There's very significant database heterogeneity. There's very significant parameter sensitivity. So these design choices that I mentioned, you would like it to be the case that the analyses are fairly robust, that you get much the same answer no matter how you set those knobs. The short version of this story is that, alas, there's a lot of parameter sensitivity. It really matters which variables you use to match and which variables you put in the logistic regression and how you define exposure windows and so on. Some of these parameters can be very important in certain analyses. And that's a little scary because right now those design choices come from here. Right? There's no real objective way to make these design choices. We're relying on what I increasingly believe is very fallible human judgment to make these kinds of design choices. A final lesson from this piece of the work, let me just do this. So as with I mentioned the coverage of 95% confidence intervals is far from nominal. Similarly with p-values, if you look at type 1 error rates at a nominal 5%, the type 1 error rates are typically in the 40 to 60% range, which is very problematic. So I want to kind of shift gears a little bit here. I want to focus on, okay, what can we do about this? And what I'm about to show you is one sort of baby step towards maybe using high throughput methods in this context to come up with approaches that have something like nominal properties. So we pursued the following approach. I'll just ground this in an example. Here's a published paper on the causal association between clopidogrel and GI bleeding. These authors found an odds ratio of around about 2, and it's highly statistically significant. The p-value in the published paper is about 10 to the minus 6 or minus 7 or something like that. So where does that p-value come from? Well, it comes from, they come up with a nominal null distribution. Right? What sort of estimates would you expect to get if in truth there was no association? And that assumes you have an unbiased estimator. It comes from the textbook, simple central limit theorem mathematics, but it assumes an unbiased estimator. And we sort of know from what I've just been showing you, that's probably not a very realistic assumption. In some sense, it assumes the problem away. So that null distribution just captures sampling variability. It does not capture bias, misclassification, measurement error, and all the other problems that we know plague these kinds of studies. Clopidogrel is way out in the tail of that distribution. That's why the p-value is 10 to the minus 6. That's the same picture, but on a different scale. You might guess why I have to change the scale. So for GI bleeding, we have about 50 drugs. We've identified about 50 drugs that are negative controls. 50 drugs that we believe do not cause GI bleeding, have no association whatsoever with GI bleeding. So if you're prepared to assume that clopidogrel is in some sense exchangeable with those negative controls, we can derive an empirical null distribution, right, that accounts for the biases and the problems and so on associated with these analyses. And so that's what you get when you run the 50 or so negative controls in this case. So you can see that the actual variability, the sampling variability is absolutely a second order issue here, right? The real uncertainty is driven by these other problems, right? The biases and so on intrinsic in these methods. And clopidogrel, in fact, is not very remarkable. You can fit a null distribution to those negative controls. You can do a density estimate or fit a Gaussian or whatever the various approaches one might take. So the p-value that we thought was 10 to the minus 6, in fact, in this case, is more like 0.3. Now, this is a particularly extreme, dramatic example, and the reason it's particularly dramatic is this particular method in this particular database, for this particular outcome, has an AUC for discriminating between the reds and the blues of about 0.52. So it's not surprising that what you think is solid evidence coming from this method, in fact, is at best very weak evidence of an association. Here's a visualization of this that is due to Martin Schumi, which I think is very elegant. So what I'm showing here is the point estimate of the relative risk on the horizontal axis. On the vertical axis is standard error. The dashed lines are nominal statistical significance boundaries at the 0.05 level. So you get to be statistically significant if you have a big, let me use this. If you have a big relative risk, you can get away with a big standard error and still be statistically significant. But if you have a small point estimate, then you need the standard error to be small in order to be statistically significant. So that's these nominal boundaries. And there should be 5% of the dots should be below the dashed line, right? These are negative controls. It's about 55% in this case. The yellow boundaries come from the empirical null distribution, right? So if you use those boundaries for statistical significance, you get something much closer to nominal type 1 error rate. So this is not so straightforward. So to do this in practice, and now several pharma companies are doing this on a day-to-day basis, to actually pursue this approach, if you want to study a particular issue, you need to develop a set of negative controls, and then you need to execute the negative controls across a range of methods and a range of databases. So in some sense, this is high-throughput epidemiology, right? But with, arguably, you could argue endlessly over the details of this, but arguably with known operating characteristics. All right, finally, in the last few minutes, let me switch gears to talk about Odyssey. So the researchers that were involved in OMOP for various reasons have regrouped under this banner of Odyssey. Odyssey is essentially an open collaboration. There are about 100 researchers around the world involved in this project. Several of the folks involved in the project have big databases mapped to the common data model. So we've built a distributed data network which now has about 600 million lives in it. It's in Europe, in Asia, in North America, and so on. We're studying a whole slew of questions, not just the question I've just focused on, which is causal inference, but we're also building open source tools that run against this common data model to consider questions such as natural history of patients taking drugs, population level estimations, what I've just been talking about. We also have a substantial project on patient level prediction. So one of the interesting uses of these data is to build patient-specific, patient-level predictive models. Although, is Jennifer here? Jennifer Hill was talking last night. It all comes back to causal inference, because why do you want to do prediction in healthcare? Well, it's because you want to predict what would happen if I did such and such to a patient, which comes right back to a causal inference question. So we're developing a suite of open source tools that you can use. Circa is a cohort definition tool. We also cohort characterization tools. We've implemented a large scale cohort method that has within it a tool called Cyclops that Mark Suchard at UCLA has been the prime mover on this, which is basically a tool that can do extremely large-scale sparse regressions, logistic regression, Poisson regression, Cox models, and so on, and is I think of value outside of this context, but also inside this context. Let me show you a great pearl. I'm going to show you a demo of one of these. So one of the tools we've developed is something called Accolades, which is a profiling tool for healthcare data, this is a live demo, so you see how this goes. So this is Odyssey. So right now the demo is working against a large-scale claims database. I'm actually not, I was trying to check this for, I'm not actually sure which one it is. But this is, it is live. So if you click on, you can do this sitting there right now. So it's a fairly straightforward visualization tool for data within these databases, and it's just one of the tools that we're developing. So what it defaults to here, you can look at drugs and other things too. This is a tree map of condition prevalence in this particular database, which contains a few million patients. So you can see, essential hypertension, for example, has a prevalence of 2% in this population. Here's one I happened to click on this morning. So this is atopic dermatitis. So about 1% of this population has atopic dermatitis. You can drill down and you see basically age profiles of this condition. So it's more common in younger people, as you can see. Not much difference between males and females. This is a picture of prevalence of atopic dermatitis since 1996 in this particular database. I just picked this one at random this morning, but you'll find this for many of these conditions. So check it out. So the prevalence was, that's 15 per 1,000 patients back in 2000, and then it sort of drifted down. But look what happened in 2007 or so, right? So there's this spike in prevalence. So it went from below 10 per 1,000 to above 15 per 1,000 in a short period of time. It seems rather implausible that out there in the population that actual diagnosis or actual cases of atopic dermatitis increased by 50% in a short period of time. So presumably this is due, and we've investigated a few of these, this is due to some other kind of secular issue out there, like coding practices or billing practices or whatever. But the lesson that that I personally have to learn every so often is look at the data. Right? So anything else in here that happens to increase that spike during that period of time will be seen to be associated with atopic dermatitis. Right? So this, these kinds of blips and issues with the data are very problematic and are of course ignored in all of the kind of analyses that I mentioned previously. So looking at the data, be it big data or not, remains sort of fundamentally important in this context. All right, that's just a plot of that. Just to kind of wrap up the last few minutes, the Odyssey network said there's about 100 researchers, many databases around the world. We're able to conceive of studies and execute studies much more rapidly than heretofore, for better or for worse. But I just want to focus on speed. So. When the FDA decides to do a study in the Mini-Sentinel database, it's a year and a half typically between the time of deciding to do a study and the time that the results, for better or for worse, become available. So with this network and this ready access to data in a common data model that is ready for analysis, and we can do things much more quickly. So I want to show you one quick example. Several of the researchers in the network are interested in treatment pathways. So with drugs, what's the first line of treatment, what's the second line of treatment, and so on, and to what extent do these conform to standard guidelines? This particular analysis I'm going to show you on the next page was conceived at AMIA, the Medical Informatics Association, on the 15th of November in a conversation. The protocol was written and the code was written and tested in about 5 days. The analysis was then submitted to the network around the world a couple of days later. And the results were submitted by the 5th of December for many of the databases that I'm about to show you. So this particular visualization is of these treatment pathways. This is for patients with newly diagnosed type 2 diabetes. And what you're seeing here is that the inner circle is the first line of treatment. So about 80% of the patients newly diagnosed with type 2 diabetes take metformin. That's what the guidelines say you should do. It's meant to be the first line of treatment. The interesting thing here is for 20% of the patients, the first line of treatment was not metformin. Right, some of them later took metformin, if you see the blue segments in the picture. But nobody's really looked at data like this before. And the point I'm trying to make is, with this resource and with a large networked database mapped to a common data model, it's possible to execute these kinds of analysis and not the other kinds of things I'm talking about in very short order. Finally, so with Odyssey, we've established this international community and global data network. It can be used, we hope, to generate reliable, reproducible evidence with known operating characteristics. We're not there yet. The common data model is critically important to all of this. It's sort of the glue that makes all of this work. Because if these databases are all in different formats and so on, this kind of work would obviously be impossible. It seems to me much work remains in terms of establishing the actual operating characteristics of the methods we use. We've put a toe in the water, but we absolutely have to stop publishing and using statistical artifacts that don't mean anything, and we're just fooling ourselves. Thank you.
Wonderful, if terrifying. Any of us who are on drugs might want to go off them right now. Let me ask you, you mentioned getting better confidence intervals through empirical explorations using negative controls. And I'm wondering how that works. If you, do you want the human biases that are producing distorted results to be the same in the negative controls as the real ones? So how do you arrange that the people believe when they're carrying out these studies that you call negative controls that the biases are the same?
So the assumption is that the biases and problems that are baked into these kinds of methods will be at the very least exchangeable across the negative controls. So there's no particular reason to believe that your drug of interest will behave a priori, will have higher bias or lower bias than this collection of negative controls. It's a leap of faith, though. It's an untestable assumption, and one could have a vigorous discussion about how we chose those negative controls and the veracity of those negative controls. One line of work that we have been pursuing, this is with Sandra Greenland, is basically adding an adjustment factor for the fact that some of these negative controls might not be. So adjusting for that in the empirical confidence intervals and p-values that I described is one way of thinking of attacking that.
Fabulous talk, Dave. Thanks. In the last graphic that you showed that characterized sort of common practice, is there metadata associated with each of those data points? So to try to help better understand, for example, why metformin isn't used in all cases?
Yeah, I'm not sure if this is live on the website yet, but this is interactive, so you can drill down on one of those segments and do a cohort visualization of the cohort that you're looking at.
Okay, and that contains rich metadata. So, like, can I know if these were people who were taking lots of other drugs?
You certainly can in principle. I'm not entirely sure if we're there yet, but yeah, there's no reason why one couldn't do that.
Any other questions? Oh, you want?
It's very interesting. So one thing I didn't completely understand, maybe you said it, so is this data, or how much of this data is available if someone wants to go and work with it?
So essentially none of it, right? By which I mean none of these data are on a public website somewhere, and for actually probably good reasons. So these are de-identified healthcare records, but they're easily identifiable with a bit of work. So that there are real concerns there. However, the way that we've been developing the Odyssey network, and this is a work in progress. There's some issues to be ironed out, but basically the way we're doing this right now is the data owners in the Odyssey network who have mapped their data to a common data model. We put a query out onto the network of researchers. Those who are interested voluntarily can run that query on their database. And we've come up with a reward system whereby you get higher priority. If you run other people's queries on your data and return it to a coordinating center, you get higher priority in later queries that are sent out to the network. We're beginning this to see how well this actually works, but it may be one way to deal with this issue, or piece of the puzzle.
Yes. One more question?
Thank you so much for this wonderful presentation. For the Achilles visualization, can somebody upload their own data, or is there like open source code that like you can run locally to see, like visualize your data in this particular way?
So the crucial thing is mapping your data to the common data model. So all of these tools work against the common data model. So we have an extensive library of ETL type tools that map. That in any particular case would need some tweaking and tuning, although we've now done about 50 databases. So we have an extensive library of ETL tools that make it fairly straightforward to map a database to the common data model. And then once it's in the common data model, then you can certainly use the tools against the data.
Excellent, thank you.
Okay. I think we're scheduled now for a half-hour break. It's 10:05, so we'll start at half an hour from now.